Extending pavement life through the use of hard aggregate. This is a presentation created by Daniel Dahms and Matthew Iskra. This presentation is directed to beginning-level undergraduate engineering students with the objective of educating a class how professional engineers can use hard aggregate as a means of extending pavement life. Why is developing new technologies to extend pavement life important? The simple asphalt pavement structure is divided into four main sections. The hot mix asphalt, or wearing course, is usually 2 to 4 inches on top. The base course is the course right underneath it, which is composed of crushed aggregate. This is usually 6 inches. The sand and gravel subbase, which is composed of well-draining material, can vary in range depending on the subgrade. And finally, the subgrade is the native soil underneath the subbase. The hot mix asphalt of major Alaskan highways, such as the Glen Highway and the Seward Highway, degrades sooner than the underlying courses. Rut depths and the rutness of the road exceed federal allowable values, and because of this, new construction projects need to be planned sooner than would otherwise be necessary. Therefore, in order to extend performance life of Alaskan roadways and provide cost savings, it is important to research the possibility of using hard aggregate. If the utilization of hard aggregate can extend the top wearing course of the pavement, then the performance life of the whole pavement structure will be dramatically increased. Hot mix asphalt is composed of two substances: aggregate, the rocks, and binder, oil. Hard aggregate is a harder, more durable version of normal aggregate. Hard aggregate are typically fine-grained without foliation. They're normally older and metamorphic or igneous rocks. The best suited for hard aggregate in Alaska are hornfels or basalt. Some sources for hard aggregate in Alaska are gravel pits located in Jervis Inlet, Dew Point, or Cantwell. One of the most popular tests for determining if aggregate should be classified as hard or normal aggregate is the Nordic abrasion test. The Nordic abrasion tests how hard an aggregate is and consists of rotating the aggregate in a drum with abrasive steel balls and water. The aggregate is massed, and then the aggregate undergoes 5,400 rotations at 90 RPM for 1 hour with 7,000 grams of steel balls. A Nordic abrasion value is then calculated using the following formula. A sub n equals 100 times m1 minus m2 divided by m1, where m1 is the dry weight of the sample before the testing, and m2 is the dry weight of the sample after the testing. According to a study by Horvely and Varnes and VTI, the Nordic abrasion values are correlated to studded tire resistance with an R-squared value between 0.93 and 0.94.
Prall testing most commonly simulates studded tire wear. The Prall test is run on 3 cores, 100 millimeters in diameter, 30 millimeters in length. First, you need to determine the bulk density. The cores need to be conditioned for 20 hours at 5 degrees Celsius, and then you insert it into the mold. 40 steel ball bearings impact the core using the machine at 950 revolutions per minute for 15 minutes. During the test, the cold water flows over the sample to simulate our cold conditions. The results are reported as a volume lost in centimeters cubed. On the left, you see a schematic and a design showing the Prall testing machine. On the right shows the classifications of Nordic countries using Prall results. And what we're wanting is the best wear resistance for studded tires. So we're looking for either a Class 1 or a Class 2 for the best wear resistance against studs.
Here are some Prall and Nordic abrasion values that some historic different mix designs have achieved. As you can see, the hard aggregate is only second to type R. The type R uses crumb rubber and a modified oil to achieve this low of a prol value, but from field testing has been seen to not preserve pavement life as well as using hard aggregate. Therefore, based on lab results, the hard aggregate should do the best against studded tire wear.
Materials matter. So hard aggregate has a Nordic value of less than 8. What we're looking at in this slide is we're looking at the gradation versus the prol value. What we did is we took a PG 5834 at 5.4% asphalt content, and we are looking at the different gradations of using either a mix of local or hard aggregate or a combination of the two. So on the right we have 100% local aggregate. Going to the left, it is ½ inch plus is hard aggregate and the rest is local. In the center it is 3/8 plus is hard aggregate, then number 4 plus is hard aggregate, and then 100% hard aggregate. You can see that once you get to the larger portion of the gradation is all hard aggregate, you start to get some very good prol values. So about 20 for the number 4 plus, you're looking at a little over 18 on the 100% hard aggregate. Asphalt content versus prol. By taking a look at this slide, you can see 4 different mixes. We see that we have 3 mixes with local aggregate and 1 mix with hard aggregate. So the hard aggregate mix for the 5834 modified was the best for its class, best over the 2 using local. However, the best actual mix was the 6440 with the local aggregate. However, we did not test a 6440 with the hard in this specific case. But really what this slide is showing, that when you add more binder and you have less voids, you're going to have the lowest amount of prol.
Because hard aggregate had seen success in other countries such as Finland, and had also achieved outstanding test results in the Nordic abrasion and prol tests, in 2013, the Alaska Department of Transportation enacted a hard aggregate policy. This policy required the use of hard aggregate on all projects that experienced studded tire wear and had an average annual daily traffic of greater than 5,000 vehicles per lane. On the following slides, some data will be presented on the tests of using hard aggregate in Alaska.
Egan Drive local versus hard aggregate. What we're looking at is a PMS data of rut for 2 different projects that occurred on Egan Drive. The first was of local aggregate and the second was of hard aggregate. Now when you're looking at the significance of PMS data, what we need to know is at 12.5 millimeters we start looking to design a project. And then at 19 millimeters we need to take a course of action, whether it be a mill fill or an overlay. So in the first project it lasted about 5 years and it was at 6.5 millimeters of rutting and our wear rate was about 1 millimeter a year. Now the nice thing on the hard aggregate is it was down for just about 13 years before we needed to trigger a project with a wear rate of about 0.8 millimeters a year. Egan Drive predicted rut depths local versus hard aggregate. What we're looking at here is an extension of our PMS data. What we did is take our rut values, our average rut values per year, and extend them out for 5, 10, 15, 20, 25 years. Our hard aggregate did the best, not needing to start designing a project till 15.5 years, where our local aggregate needed either a project to be designed at either 10.4 or 12.5 years. The problem with this is our design life for projects is usually a minimum of 10 years, anywhere up to about 20. The greatest significance of the hard aggregate in this situation is that Immediate action is not needed on the hard aggregate until 23.5 years, which gives us an increase in life of about 4 years. Tudor Road results, local versus hard aggregate. Here we can see the PMS results of Tudor Road. What the project did was it took the eastbound lanes and used hard aggregate in the mix, and the westbound lanes used local aggregate in the mix. On the westbound lanes, it took 9 years to hit 12.5 millimeters, and to hit 19 millimeters for immediate action, it took 15 years. The eastbound hard aggregate lanes took 13 years to hit 12.5 millimeters to design the project, and then 20 years for 19 millimeters needing immediate action. What this data tells us is we have gained between 4 and 5 years worth of life using hard aggregate on the eastbound lanes of Tudor.
We conclude, based on the laboratory and field data, that hard aggregate can be used by professional engineers as an effective means of extending pavement life. In South Coast, the pavement saw an increased lifespan of 4 years. On Tudor Road, the pavement will barely meet the 10-year lifespan using local aggregate, but using the hard aggregate is estimated to last 14 years. Due to positive lab results and field results, the continued use of hard aggregate is suggested on roadways with an average annual daily traffic greater than 5,000. Also, it's recommended to use hard aggregate as needed on roads with an ADT of less than 5,000, but that are showing premature wear due to studded tires. This concludes our presentation. We hope you enjoyed it, and feel free to leave any questions in the comment section below.